All right. In this video, I'm going to overview the procedure sections for Lab 6. There are two sections, A and B. In Section A, you're going to measure the size, the diameter of our galaxy, the Milky Way galaxy, and determine our position in it relative to the center. In Section B, you're going to measure distances to and sizes of a handful of spiral nebulae, and you're going to do this in two parts. In part 1, you'll observe these spiral nebulae with Skynet, and in part 2, you'll measure their distances and sizes. Okay, let's go into Section A. In this section, we're going to use globular clusters, which are distributed in a large halo about our galaxy, to determine our position in the galaxy and the size of the galaxy. In total, there are about 150 of these out there, but we'll only need about 30 of them to do this exercise. So I've selected 30 of them randomly, and they're listed in this table here. And for each one, we begin by listing its sky coordinates. And we do this in the galactic longitude, galactic latitude system. That's described in this figure here, where galactic longitude 0 and galactic latitude 0 corresponds to looking towards the center of the galaxy. Galactic longitude changes in the plane of the galaxy, and galactic latitude measures how many degrees you're above or below the plane of the galaxy. Here it is from Earth's point of view. The galactic center is here in the middle at galactic longitude 0, galactic latitude 0. Again, longitude changes in this direction, and latitude changes in this direction. Now, for every globular cluster listed in this table, we've identified an RR Lyrae variable star. And in Lab 5, you learned how to use these stars to measure distances to the star and hence to the globular cluster that contains it. In this column, we've listed the average apparent magnitude, in other words, the average brightness, little m, of these stars. In this column, you need to enter the average absolute magnitude, in other words, the average luminosity, big M, of these stars. And if you can't remember what that is, you can find the value in the background sections of Lab 5. Once you have little m and big M, you can calculate the distance to the star and hence to the globular cluster. And the equation for doing this is also in the background sections of Lab 5. Now, there are 30 entries in this table, so that's a lot of calculations. But in this video, we show you how to do all these calculations at once, or at least much more quickly, using a spreadsheet. Knowing the basics of how to use a spreadsheet, how to program equations into a spreadsheet is a very valuable skill in general. It'll make your life a lot easier in this lab as well. Once you do this, you'll have the distances to all of these globular clusters. You'll present a sample distance calculation here, and then you'll go to our graphing website and select Scatter. This is where you're going to make the top-down map. As if you were above the plane of the Milky Way galaxy looking down, you're going to plot the distribution of these globular clusters using the sky coordinates, galactic longitude and latitude, and the distances that you just calculated. And how to do that is described in this tutorial here. Once you've done that, you want to save your top-down map as a PNG file and upload it to WebAssign here. Once you've done that, you can use this plot to measure the distance between us and the center of the globular cluster distribution, and that will be the distance between us and the center of the Milky Way. You can enter that here in kiloparsecs. Look up the true value, enter it here, calculate a percent error, which goes here, discuss sources of error here, and then answer this question. Who is more correct about the solar system's place in the Milky Way? Shapley or Curtis, or neither? Okay. Then we'll again use this plot to measure the size of the Milky Way galaxy. And for that, you're just going to measure the size of the globular cluster distribution. Enter that here in kiloparsecs. Look up the true value for the size, the diameter of the Milky Way. Enter that here in kiloparsecs. Calculate your percent error and discuss sources of error here. Then answer the following question. Who is more correct about the size of the Milky Way? Shapley or Curtis, or neither? And for this, don't think about it in terms of differences. Think about it in terms of factors. Shapley was off by a factor of what? Curtis was off by a factor of what? Okay. Then let's go to section B of the procedure. And in part 1, we're going to observe a handful of spiral nebulae. We've selected some for you, distributed around the sky, meaning that at any given time of year, probably 3 or 4 of these will be observable. Sometimes all 5 might be. Observe as many as you can. These are simple observations in Skynet. They're not repeating. They all use the high-through filter. They're all 80 seconds in duration on the generic telescope, and you should restrict yourself to prompt telescopes for this observation because you want that higher image quality. Now, hopefully, you've already put in these observations about a week ago, and you're ready to move on to part 2 of section B. In this part, you're going to calculate the distances to and diameters of the spiral nebulae you just observed. First, in this column, indicate whether or not you got an image back from Skynet, yes or no. If you did not get an image back, do not do the calculations for that spiral nebula. Only do the calculations for the spiral nebulae that you observed. Now, for each of these spiral nebulae, we've gone ahead and identified a Cepheid variable star in the spiral nebula. And in the previous lab, lab 5, you learned how to use Cepheid variable stars to measure distances to the star and hence to the spiral nebula that contains it. In this column, we've listed the average apparent magnitude, in other words, the average brightness, little m, of that Cepheid. Here, we've listed the period of the Cepheid in days. Now, in this column, you need to calculate the average absolute magnitude, in other words, the average luminosity, big M, of the Cepheid. And the equation for doing this is in the background sections of the previous lab. Once you have little m and big M together, you can use them to calculate the distance to the Cepheid and hence to the spiral nebula. And you list those here in kiloparsecs. Again, only for the ones that you observed. Then you have an honor code pledge and 2 sample calculations. The first is for the average absolute magnitude given the period, and the second's for the distance given little m and big M. Then watch this tutorial on how to measure the angular diameters of the spiral nebulae that you observed using Afterglow. There are a few reminders here, but then enter your angular diameter measurements in arc minutes in the table here. And again, only enter numbers for the objects that you were able to observe. In this column, you'll convert from arc minutes to degrees. And then in this column, you'll calculate the true physical size of these spiral nebulae in kiloparsecs using the equation from the background sections. You'll do a sample calculation here of the diameter of one of your spiral nebulae. discuss significant sources of error here. And then we have two questions. How does the size of the Milky Way, which you measured in the previous section, compare to the sizes of the spiral nebulae in your sample? Is the Milky Way many times larger or many times smaller or typical of the diameters of the spiral nebulae in your sample? Lastly, who is more correct about the Milky Way's place in the universe? Shapley, Curtis, or neither? Okay, that's it for this video.